Okay, thank you everybody coming. Welcome to our EOL seminar. I apologize. I'm not sure if I saw any refreshments out front there. I think we might have had a little mess up on scheduling which room we were going to be in. So anyway, our speaker today is Minghui Diao from San Jose State University. She's assistant professor at the Department of Meteorology and Climate Science there. She took her undergraduate study at Peking University in China, and in 2013 she received her PhD from Princeton from the Department of Civil and Environmental Engineering, working under Mark Zonlo. Has been involved in many field campaigns such as the Orca, Hippo, the DC-3, the Predict campaigns. Mostly those have been run out of RAF, out of Broomfield. She was, where am I? She has an ASP postdoc fellow at EOL, working with Jan Jensen at the time. And among her awards, she's had the ASP Faculty Fellowship, a NASA NESSF Graduate Fellowship, the Francis Upton Fellowship, and the AGU Outstanding Student Paper Awards for both 2009 and 2010. So please welcome Minghui Diao.
Okay, everyone. Thank you all for coming, especially during summer. So today I'm going to show you some of the work I did with my two students here, Katie and John. And the title of my talk today is Ice Cloud Formation, from in-situ airborne observations to a hierarchy of models. I would like to acknowledge my collaborators, especially Dr. Jan Jensen from EOL, who has also been my postdoc advisor when I was an AFP postdoc. And also, I want to acknowledge all the science teams of DC-3, Contrast, Orcas, as well as the instrument PI, because this is a collaborative work. We couldn't do this work without all the support. So here's my outline. I want to start with the importance of understanding ice supersaturation, because it's the birthplace of cirrus cloud formation. For observations and model simulations, I will use a series of flight campaigns from 2008 to 2016, and they are all on board the NSF Gulfstream 5 aircraft. In addition, I will use a NASA HVAC campaign happening in 2014. For the hierarchy of models, I will use WRF, the NCAR CM1 cloud resolving model, and CAM5 model. There will be 4 sections in my analysis. The first one is the radiative impacts of ice supersaturation based on observations of 5 campaigns. The second one is the dynamical condition of ice supersaturation in convective systems, which is comparison between DC-3 and WRF. The third section will be the analysis of chemical tracer and relative humidity in the TTL from contrast and ATRAX. The fourth section will be the comparison between observations CM1 and CAM5. In the end, I'll give you my conclusion and future work. So I'm sure most of you are very familiar with this picture, but I want to emphasize one point here. It's actually a comparison. If you look at the sum of all the anthropogenic greenhouse gases, you will get a value of 3 watt per meter square. And if you compare this value to the global cloud net forcing, which is a negative 20 watt per meter square, it means that you just need to change 15% of the global cloud radiative forcing, and you can either double or cancel out all the anthropogenic greenhouse gas effects. And unfortunately, the problem now, as you can see, is the cloud adjustment due to aerosol are still highly uncertain for the climate prediction. Among all the type of clouds today, I will focus on a cloud which is called the cirrus cloud. It is located at relatively higher altitude. It's usually around the upper troposphere and around the tropopause, and is almost entirely composed of ice crystals. For the birthplace of cirrus cloud, it has a special name. It's called ice supersaturation. It's the prerequisite condition for ice crystal formation. And in the observations, when we want to measure ISS, we just need the water vapor measurement and the temperature measurement to derive the saturation vapor pressure with respect to ice. And now I give you a diagram from Peter et al. 2006, published in Science. This diagram describes a few phenomena that you could observe in the real atmosphere. The first one is a conventional nucleation and growth. That is, when you have an air parcel, you lift it up, and as being lifted up, the temperature will cool down and the relative humidity will go up. So as a result, the relative humidity will eventually hit the threshold for homogeneous or heterogeneous freezing, and then ice crystals will form and relative humidity will come back to 100%. However, in the real atmosphere, it has been frequently observed with these two conditions. One is the suppressed nucleation, which means you can have RH already reaching the threshold for nucleation, but it's still in clear sky and no ice crystals have been observed. Or you can see suppressed growth, which means you have ice crystal being formed already, but there are still supersaturation coexisted with them. And the bigger question is, how often do we see these three conditions? And to quantify that, we want to know how do we see the magnitude and the frequency of ice supersaturation in our observation, and how about their spatial characteristics and microphysical properties. So now, you probably are still not convinced, why do we bother to present ice supersaturation in model? One perspective I want to show is from the radiation perspective. On the left-hand side, you have a cirrus cloud, which is a fake cirrus cloud in the model. By fake, I mean it should have been ice supersaturation, but you actually put in this cloud instead of having the supersaturated part. On the right-hand side is a clear sky ice supersaturation. So the fake cirrus cloud would block some of the short-wave radiation and trap some of the long-wave radiation. But for clear sky supersaturation, it's just water vapor. It doesn't block much of the short-wave radiation at all, and it still traps the long-wave radiation. And the difference between these two, as done by Fusina et al. 2007, using an idealized scenario, they concluded to be a 3 Kelvin per day difference. And remember, this is only an idealized calculation. And now, the good news is many of the models, from GCMs to cloud resolving models, all started to include supersaturation in their simulation. But how do we validate and improve them? That requires we have more observations and more comparison studies to evaluate and improve these analyses. And talking about observations, here is the instrument that I will be using. It is called the Vertical Cavity Surface Emitting Laser VCSEL Hygrometer. It is a water vapor hygrometer working at near infrared region, 25 Hz, and all the analysis will be averaged to 1 Hz data. It has an accuracy about 6% and below, a precision of equal below 1%, and it has an advantage in its inherited design. So when it's being designed, it uses 2 absorption lines. One is a strong absorption line, the other one a weak absorption line. So it can automatically measure from 1 ppmv to 40,000 ppmv by just this one instrument. And it also has an open path system, as shown here. This blue fin is what is hanging outside of the Gulfstream 5 aircraft. And here are the optical paths between the upper and lower mirror. You don't have issues of water vapor sticky to the closed path inside wall because this is the open path design. And with the most recent QC/QA temperature data, we actually can achieve about 7% to 8% uncertainty in relative humidity for the whole temperature range we measured in the NSF G5 campaigns. So now I want to show you why it's important we use in situ and accurate measurement for water vapor. Here is a study I did in 2013 validating the NASA Air's water vapor and temperature, and I found that 40% water vapor difference and about 1 to 2 Kelvin temperature differences are seen in Air's data compared with the HAPO campaign for the UTLS region. So now with this type of measurement, we can do a lot of things. And in this summer, my student and I were hosted by EOL and also under the funding of ASP Faculty Fellowship. We have been doing series of modeling analysis and laboratory result calibration. So I'll show you all of them. Now let's start with a radiation calculation. The first thing I mentioned before is an idealized scenario show you can have a large impact for ice supersaturation. But how does the real observations quantify this kind of impact? Here we use 5 in-situ measurement, 5 flight campaigns: HAPO, STARO-A, DC-3, PREDICT, and TORERO. And every flight campaign provides those one-dimensional sampling of supersaturation. And then we insert these one-dimensional sampling into the ERA interim data, which provides the column-wise information. In each column, you have temperature, pressure, specific humidity, and then we can plug into the rapid radiative transfer model, RTMG, to calculate the radiation effect. And I want to note previously, there is a study by Gettleman and Kinnison in 2007, which used the WRF global model to quantify the radiative impact of supersaturation. They only compare the scenario of including or excluding supersaturation in the model. But how about including or excluding the real supersaturation as observed? That is what we're trying to do. So if you're not familiar with the sampling range of the field campaigns, I want to show you this one from the HAPO global campaign. It has a near pole-to-pole in-situ measurement of water vapor from about 87 north to 67 south. And every 3 degrees, we have a transect. So the gray color line actually shows the real flight track of G5. And I color-coded the water vapor measurement on log scale. So red means more moisture air, and the colder temperature upper here has the drier condition, which is in blue. So with this kind of sampling, we do the radiative impact analysis. We want to know what kind of a difference it will make if we misrepresent supersaturation as fake ice clouds. So now we just plug in artificially added ice crystal into the model, RTMG model. So one condition, we have artificially cirrus compared with supersaturation in clear sky in the observation. The other condition is we used to have supersaturation in cloud, and now we add even more ice crystal to replace the supersaturation. So these two impact types, we have about 3,000 samples, and each sample, please note, is not a 1 second sample. It can range from hundreds of meters to hundreds of kilometers. So each sample is a domain, is a region. And with 3,000 clear sky sample and about 900 in-cloud sample, here is our average result. Misrepresenting the clear sky supersaturation as artificial cirrus can have a maximum TOA net radiation of 54 watt per meter square, and it can have an average TOA net radiation impact of 4 watt per meter square. Now, if you still remember in the beginning, I talked about the 3 watt per meter square, which is the sum of all the anthropogenic greenhouse gases, you can actually have a scale comparison. What is the influence of this type of misrepresentation? And similarly, the impact type 2 has about the same orders of magnitude of radiative impact. And I want to also mention the surface net radiation on average will be a negative 3.6 watt per meter square, and heating rate on average is about 2 Kelvin per day impact. So now we go to a sensitivity test. So does the radiation only have the same magnitude of impact regardless of the microphysics? And the answer is actually no. It's highly sensitive to the pre-existing ice-water path. So the pre-existing ice-water path is the one that used to already coexist with the supersaturation. And we did 2 idealized scenario comparison. And please note, even though this is idealized scenario, it's actually representative of the average condition we see in 5 campaigns. So in the first scenario, we have a pre-existing ice-water path of 42 gram per square meter. The second one is 60 gram per square meter. So with a slightly lower ice-water path, if you just focus on this black line, this is the net radiated impact, which is the sum of the short wave in blue and the long wave in red. So this net radiative impact are dramatically different if you compare these 2 pictures. So that means you have a very dramatic sensitivity to how much pre-existing ice is already there to determine how effective if you misrepresent these supersaturation, would conclude. Now, coming back to the 5 flight campaigns, you can also see this type of sensitivity. This is the TOE radiative impact of misrepresenting supersaturation. Some of them are positive value, but as you can see, once you cross a threshold of ice water pass, you will actually flip the sign of the impact from positive to negative. So we're talking about not only you have to represent it, but you have to be able to represent the coexistence between supersaturation and ice crystals. So now come to my student John, his analysis, which is the dynamical condition of ice supersaturation in convective systems. We're using DC3 campaign to compare with a series of WRF simulations. Now, for the DC3 campaign, we mainly used the G522 flights, and it happened in May to June 2012. We also did a sensitivity test with the NASA DC-8 aircraft, and I just want to already point this out. The conclusion doesn't get changed between the different aircraft platforms. And for WRF simulation, we used the realistic case simulation, and we also tested different days. It doesn't influence our result. And for the horizontal, we use 2.4 kilometer, as I'm going to show you, but higher resolution at 800 meter also shows very consistent result. So what I'm getting at is, you can see I'm not trying to do a case-to-case comparison. I'm not trying to replicate the same case, capture the exact same storm in WRF. What I care about is if WRF can actually capture the general physics, such as the correlation between supersaturation and vertical velocity. And this correlation should be very consistent among different simulations of WRF and among different research aircraft sampling at different days and by different instrument. So with this type of comparison, I'm trying to evaluate 4 double moment microphysics schemes. The first one is the default Morrison double moment scheme. The second one is where we modify the Morrison scheme by increasing the Cooper parameterization threshold from 108% to a new value of 125%. The third one is the 2008 Thomson scheme, and the fourth one is the Thomson-Eidhammer 2014 scheme, which include heterogeneous freezing of ice crystals. So here is one of the realistic case that we're sampling, which is a squall line scenario happened on May 19, 2012. And here is the domain of the DC3 campaign. Now, first thing is to see, can these microphysics schemes capture supersaturation? If you look at the relative humidity with respect to temperature, in observation, for in-cloud sampling, we mostly center around 100% relative humidity. This is very consistent and has been frequently observed in many field campaigns. And for clear sky condition, we see a wide range of distribution from about 10% relative humidity to 150%. Can the microphysics scheme represent the concentration around 100%? Yes, most of them represent this concentration in cloud at 100% RHI. But the variability seems to be a bigger issue. So we can see in several of the schemes that actually included the Cooper parameterization, there seemed to be a cutoff here at 108%, here at 125%, and here at 125%. That is exactly where Cooper parameterization is actually initiated. And the last parameterization, which doesn't have Cooper parameterization, so far has the closest PDF of RHI compared with the observation. So please keep in mind, how does Cooper curve actually influence the other simulations as I'm going to show. So another comparison is the correlation between supersaturation and vertical velocity. We want to know if the simulations rely on vertical velocity to generate supersaturation. And if so, how strongly do they rely on vertical velocity? And before we do that, we need to control 2 factors, ice water content and vertical velocity. The higher ice water content you have in the model gray box, the harder it will be for the model to maintain or generate supersaturation. So we have to first control ice water content on the y-axis. And then we group the vertical velocity into different colors from the downdraft, the small updraft, all the way to the red color, which is the very strong updraft. And if you look at the color line, if they are very closely to each other, like this one showing in DC3, the left upper corner, it means there's not much difference in the ice supersaturation frequency for these different vertical velocity. And if they get separated apart dramatically, it means the higher vertical velocity here, for example, the red color here, has a much higher chance to see supersaturation than the smaller downdraft. And I want to cut it into two pieces. So the conclusion are twofold. If you look at the high ice water content, greater than 0.1 gram per cubic meter, simulations show ice supersaturation frequency significantly higher in the higher vertical velocity, such as here, the red color, compared with the lower vertical velocity, which is, say, the blue, the dark blue, or the black, or the yellow, which is here. And the orders of magnitude is about 4 orders of magnitude of difference. But the observations only show 1 to 2 orders of magnitude of difference. So stronger dependence is shown for vertical velocity in simulation. And the second fold I want to show is how about the lower ice water content? Now the story seems to change. When you talk about lower ice water content, it's very interesting that the high vertical velocity start to show lower supersaturation frequency. It seems a little bit counterintuitive, and for why it happens, we're still trying to figure out. But this is quite consistent with the Morrison modified scheme, the Thomson scheme, and even the Thomson aerosol aware scheme. And now we move on to another type of comparison. Instead of constraining it by vertical velocity, how about showing the whole domain of vertical velocity? And I want to acknowledge, we know that the aircraft cannot sample the most dramatic updraft or downdraft, especially in the convective core. So we cannot do that. But this is the domain of the vertical velocity in DC3. And if you stretch out to the right-hand side in simulation, it means all these extremes of vertical velocity hasn't been sampled by the observation. But if you look at the correlation, which is highlighted by the yellow color where the high occurrence frequency of supersaturation occur, with the x-axis, which is the vertical velocity, the slope of this red dashed line indicate how strong the correlation is. If you have a more tilted slope, like almost all of the simulations show that, it means you have a stronger dependence on vertical velocity in order to generate the supersaturation. And another thing still, if you have Cooper curve parameterization initiated, there is a chance that there will be a lack of higher relative humidity due to the Cooper parameterization. So move on to my student Katie's work. So we're also looking at ice supersaturation in the tropical upper troposphere and tropical tropopause layer. So the DC3 campaign happened in the extratropics. And now we use the 2014 NSF contrast campaign, which is in yellow, and the NASA ATRAX campaign, which is in red, to show how the sampling around Guam actually can capture supersaturation. And I want to do a comparison from the MLS data. This is the MLS data at 215 hectopascal, and it shows very high occurrence frequency, around 30% for supersaturation at this level. So we're talking about a region that has high frequency of supersaturation. And I want to answer the question, or still trying to figure out, what factors affect the partition in ice supersaturation in and out of clouds in the tropical UTLS. So the first graph is, all these pictures are from NASA ATRAX 2014. So the first picture I show is the frequency occurrence of supersaturation. If it has gray color, it means that we do have sampling, but there's no supersaturation being observed. If it's red, there's a little bit supersaturation. Till purple, there is a lot of supersaturation being seen. So the highest frequency happens around the coldest temperature at the TTL, which is very consistent with my 2015 paper studying the extratropical tropopause, where around the extratropical tropopause, a lot of high frequency of supersaturation is observed. But what is interesting is the partation. How much supersaturation stay in clear sky? How much of them convert to be with cloud? So here's a ratio between clear sky supersaturation and the total supersaturation, which is clear sky plus in cloud. If you have red color, it means all these supersaturation are mostly with ice crystals already, and they seem to have a clear cutoff around minus 68 Celsius, and is also associated with relatively higher CO concentration. Why is that? I speculate this is probably convective influence, but why there is a clear temperature cutoff, I have to study more about that. And also at the top of the global Hawk sampling, you see a higher frequency of clear sky. So now this is quite important. As I say, you have to understand how supersaturation coexists with ice crystals. It coexists at the warmer temperature, but it becomes clear sky at the top. Can we represent this in model simulation is something I'm still trying to figure out. And the vertical velocity is highly associated with these two clear different regions. So the vertical velocity is slightly higher, associated with the higher ozone and more convective region, while the vertical velocity in the upper level is slightly lower. So for the vertical velocity correlation, contrast has shown very similar correlation. So this is what Katie has done. She looked at the average vertical velocity from -1 to 1 meter per second. So the supersaturation above 100% has a more yellow color, which means you have a higher average vertical velocity. And if you only plot the average vertical velocity greater than 0, you can see how they all show up mostly around 100% and above. And now for the frequency of updraft, how frequently do you see updraft? It's also more frequently seen in where relative humidity is greater than 100%. So what I'm getting at, in the TTL, vertical velocity seems to have a correlation with how supersaturation occurs and how it's partition between clear sky and in cloud. And another thing that Katie has been looking at is to compare the chemical tracer correlation with those simulated by WRF-CAM. So this is our preliminary WRF-CAM simulation at a very coarse resolution of 10 kilometers. We're planning to do higher resolution. But so far, we can see the potential temperature signature at the dry condition compared with the moisture condition can be captured by WRF-CAM. You have this higher potential temperature, about 370, compared with the lower potential temperature in the more moisture regions at 350. And so far, this has been seen in the WRF-CAM as well. So this is very preliminary work, but I just want to show you. And now, as I say, there's another model I want to look at. So besides WRF, which we do at 800-meter resolution or 2-kilometer resolution, how about we use a cloud resolving model, use a much higher resolution to compare with aircraft observation. So here I use the CM1 cloud resolving model at 250 meter, 1 kilometer, and 4 kilometer. These are the cross-section of an idealized scenario of a squall line. And just from the structure of where you see supersaturation in the green color, it's very patchy, which actually is more representative of what we're seeing in the real observations. To quantify this, I have to do a more apple-to-apple comparison. So how do I compare a 3-dimensional sampling of the CM1, which is a 3-dimensional non-hydrostatic numeric model, with 1-dimensional aircraft? So George has helped me to put in the mock aircraft in the CM1. We put in a mock aircraft in every isobaric level by 1 hectopascal. We put in about 450 fake aircraft. And all of them will continuously sample inside CM1. And with this kind of one-dimensional sampling, we can plot the spatial characteristics of ice supersaturated region. Here is one Hertz observation, and the other panels are different resolution simulation, 250 meter, 1 kilometer, 4 kilometer, or using different microphysics parameters, such as increasing the Cooper parameterization threshold and using exclude the Cooper parameterization once for all, or you have a smaller deposition rate of water vapor, or you have a smaller ice nuclei number concentration. And all of these simulations are using Morrison double moment scheme. So the result shows that relative humidity is correlated with the length of supersaturated region, which means the larger length you have, more likely the relative humidity in there, the maximum number, and we also did the average number, will be higher. So larger domain, more likely to have high RH, and also subsequently more likely to form ice crystal because of that. So can CM1 represent this correlation? This correlation, if I do a linear fit, I'll get a slope of 12.68. And if you compare with the slope of all the other tests, you see the closest one we have is when you alleviate the initiation of Cooper parameterization to 130%. And now, if I do another comparison, how does supersaturation get formed? What is the formation mechanism in observation compared with that in CM1? In observation or in simulation, fundamentally, you have two ways to form a supersaturated region. One way is you have more water vapor in there. You have a box, you put in more water vapor, and compare with the outside, it will have a higher RH. Or you have colder temperature in there. You cool it down, same amount of water vapor, but it'll still have higher RHI than outside. And what you can do is to quantify it with this total derivative equation. So I quantify into a water vapor contribution and a temperature contribution to how supersaturation is formed. And now the observation, every single blue dot or red dot represent a supersaturated region. And I do the comparison with its adjacent neighbor. So the slope of the blue dot is 0.92. That means water vapor spatial heterogeneity contribute to 92% of the higher relative humidity inside the ice supersaturated region. And temperature only contribute to about 0.08, which is 8%. If you keep that in mind, this is the same comparison, observation, and with all these simulations. And the good news is, if you just look at the slope, most of them are close to 1 or 0.92. So I don't have to read these for you. You can see there, the slope is generally well represented. But we're talking about large variability in the simulation, which I still try to figure out why is that. And of course, as you can see, if you have Cooper parameterization initiated, immediately cut off RHI at 8% here. But another thing that is not so promising is the ratio between supersaturation in cloud versus the non-supersaturation in cloud. So if you have a cirrus cloud, what is the ratio between supersaturated part and non-supersaturated part? The observation show the ratio is about 1 unity. And all the simulations, except alleviating Cooper parameterization, again, shows a much lower ratio at 0.65, 0.74, 0.65. So could it be that the parameterization actually underestimate how much supersaturation should have been in cloud? I try to do more simulations probably in the future to address what all kinds of simulation would represent in this way. Now move on to CAM5 model, as I promised you. Why do we care about these water vapor contribution or temperature contribution? This is actually linked to the ultimate question. If CAM5 misrepresenting or miscapturing a cloud, that has been seen in the observation but couldn't be captured in CAM5. What is the reason for that? So here I have one case study from HAPO Global Campaign. This is the flight about, I think this is over the Southern Ocean, one of the Southern Hemispheric flight. What we do is we have the real flight track, and we have the 2DC and CDP measurement. 2DC in blue, CDP in green. And the shaded square box are the CAM5 simulation with the nudge GEOS5 analysis. So we nudge the CAM5 meteorological condition with GEOS5, try to represent the similar dynamical condition as seen in the observation. And here, the blue actually captured where the 2DC has seen ice crystals as well. But for this region, we want to zoom in is because this is where CAM5 hasn't been able to capture these observed ice crystal or mixed phase clouds, ice crystal / water droplets. So to understand why CAM5 missed the clouds here, we zoom into all these fluctuations. The first one is the fluctuation of relative humidity. Blue for CAM5, red for HAPO. You miss these fluctuation of relative humidity at exactly where you miss the cloud. And now we split into the fluctuation of water vapor and fluctuation of temperature. Let's first take a look at temperature. Yes, you see a bias of temperature, an offset about 1 degree or so in CAM5 compared with HAPO. But what really matters is CAM5 lacks of these fluctuation that is seen in HAPO, which is the water vapor spatial heterogeneities that I have been trying to emphasize in my previous analysis. So why it matters? I'll give you an idealized comparison. But this is actually from a real flight track in HAPO. What I do is I get this segment of flight, and the relative humidity is in black. The blue is my water vapor mixing ratio, ppmv. The pink is temperature in Kelvin. This is real observations from G5. Now, I can either neglect water vapor variability or I can neglect temperature variability. If I neglect water vapor variability, you have this red dot dash line. You don't even have any supersaturation at all. If I neglect temperature variability, you still have some kind of a structure remaining that can see the remnant structure of the black line. And you could also argue, what if I just capture the relative humidity using a fake, artificial temperature profile or temperature fluctuation? I use the fake temperature to force the relative humidity to go up really high when it should be supersaturated. And the result would be you will have a 2 Kelvin colder temperature if you want to represent the same relative humidity fluctuation at the supersaturation, but you still want to neglect the water vapor fluctuation. So this just to give you an idea, if in the real observation, neglecting water vapor variability can lead to no supersaturation at all, in this case, we need to think about what it would do to CAM5 if the water vapor spatial heterogeneity isn't completely included. So talking about water vapor spatial heterogeneity is important. We can rely our analysis on accurate, high-resolution in-situ measurement. So this is what I have been doing since my PhD study at Princeton. So at Princeton, I used 4 different calibration systems. I'm not going to the detail, but what I try to do is to represent the real atmospheric condition in the laboratory. I try to represent pressure from 100 to 1000 hectopascal, temperature from -90 to 30 Celsius, and water vapor from about 1 ppmv to 4 to 10 times 10 to the 5th ppmv. So this provides a large sampling we have to do in our laboratory calibration. So you can see this is an enormous amount of calibration that we have to do for the open path system because it's hanging outside of the aircraft. And now, this summer, I got this very wonderful opportunity to come back to RAF, come back to EOL to do the calibration. So I want to thank Dr. Stuart Beaton, Teresa, and Dr. Steve Semmer for helping me setting up the calibration in 2 environmental chambers, one at REF, one at Foothill. And what we're trying to do is to reach temperature from 0 to -70 C at a very slow state and to replicate what I have been doing at Princeton. And we have known already in different systems, there are advantages and disadvantages. So this summer provides a very good opportunity for me to resolve some of the already well-known issues, I think. And now we're hoping, as a result of my calibration, we'll be able to apply new QC/QA data to the ORCAS campaign, contrast campaign, or even previous campaigns. So with this, the ongoing work I'm going to show is about the ORCAS campaign. So this is the campaign just happened in January to February 2016. As you can see, it provides a large amount of sampling over the Southern Ocean. Back in 2014, I wrote a paper about a hemispheric comparison on ice supersaturation using the HAPL data. I want to see if there's any difference in the clear sky and in-cloud ice supersaturation frequency between the 2 hemispheres, because it will be a good indicator to see if the prerequisite conditions for cirrus cloud are different or not between the hemispheres. And my conclusion based on HAPL data solely has no significant difference captured in the HAPL data. And at that time, I acknowledged that there must be geographical sampling issues that we have to further address. So here we go. ORCAS actually provide a very unique data set for me to do further analysis over the Southern Ocean, which is usually the region lack of sampling. So one thing I'm going to do is to compare ORCAS with CAM5. So this is the simulation using CAM5 at about 1 by 1.25 degree. And this is the latitudinal distribution of supersaturation. We have a lot of supersaturation occur in the higher latitudinal region, especially in the polar region. And the good news is CAM5 can capture all 3 scenarios. It can capture clear sky supersaturation, in-cloud supersaturation, and the clouds without supersaturation. And the ratio seems to be comparable to the 1-to-1 ratio that I have been mentioning previously. If you sum up this and compare with that, I know this is not exactly 1-to-1, but a lot of them still are being captured. So that is a good news to start. But something that isn't completely comparable with observation is when we look at the relative humidity versus temperature distribution. So ORCAS, we use 2DC and CDP probe. Whenever we have ice crystal or cloud droplet measurements, we call it in-cloud. And otherwise, we call them clear sky. So we combine RHW with RHI from the whole range of ORCAS sampling. And we compare it with the quarter degree CAM5 simulation. Everything is layer normalized. So if you see a redder or more greener color showing up, it means most of the sampling occurs around 100%. And this is quite comparable, 100%, about 100%. But what is slightly different is you can see there is a mixing line of water vapor. This is frequently observed and previously mentioned by Kramer 2009 as well. If you have a trajectory of a parcel lifting a conserved water vapor in there, you will have water vapor conserved, but relative humidity gradually go up. And this mixing line happened at a different temperature between ORCAS and CAM5. It also happened along a slightly different trajectory if you compare these 2 yellow dotted lines. So we're hoping to do more analysis with CAM5, constraining the same domain as ORCAS, but testing seasonal variabilities and latitudinal variabilities. But I just want to show you this is something interesting to test. And another thing I apologize for the cutting off, but I will tell you what happens here. So another thing we're looking at is how does supersaturation frequency correlate with microphysical properties? We're talking about mixed phase cloud now. So we have ice crystals and liquid water ice water content and liquid water content. And we also separate out where you only have ice water content or if you only have liquid water content. If we focus on this picture, the different color here shows the different range of cloud fraction. So we calculate the cloud fraction in situ data, and we have the cloud fraction output on the grayscale from CAM5. And we see how does the supersaturation frequency differ between different cloud fraction and in relation to the log scale ice water content. Well, one interesting correlation here is as your liquid water content goes up, all the cloud fractions start to show a higher frequency of supersaturation, but there's no significant correlation seen in CAM5. And another thing is, if you look at the ratio of ice water content divided by liquid water content, this shows how much of water in mass gets into ice versus gets into liquid. There is a decreasing, if you go upward, decreasing ice supersaturation frequency as this ratio goes up. Yes. So the higher ratio goes, the lower frequency it will be. And this is quite consistent for all the cloud fraction range. And you can see in CAM5, there is a very different pattern. So next step, we're trying to see why this pattern actually happen, what is going on. But I just want to show you this is exactly what we're doing right now and trying to figure out. So in the end, there's one more ongoing work that I have been collaborating with Dr. Ulrich Schumann. So we try to look at the influence of aerosol and CO concentrations on the number-weighted mean diameter of ice particles and also on ice cloud ratio. This is all using HAPO data for now. We have temperature and CO concentration. We have temperature and log scale total aerosol concentration. As you go to lower temperature, in general, you have a smaller ice particle. And that makes sense because you're probably more likely to have homogeneous freezing. And you go to higher CO concentration, there seems to be a signature that a decrease in the ice particle size is also shown in the HAPO campaign. And this is not exactly captured in the aerosol concentration. In fact, there seems to be a slight increase right here. And for the cloud ratio, if you have higher aerosol concentration, this is quite prominent feature that the cloud ratio start to go up from near zero to more close to 0.5. And similarly, in CO, higher CO, some of them are correlated with a higher cloud ratio. And I want to say this is probably one of the hardest thing to do right now for me, since you have to first constrain the vertical velocity, dynamical influences in order to understand the aerosol and CO concentration influences. And this is also an ongoing work. So with that, I would like to conclude with a few bullet points. I have shown you that it matters quite a lot to represent the supersaturation in simulations based on radiation calculation. And for WRF comparison, there seems to be a stronger dependence on updraft speed in order to represent the supersaturation. And the Cooper parameterization seems to produce a further away ice water content and concentration, ice crystal number concentration and RHI compare with those observed. For chemical tracers, we're still ongoing work. We're trying to compare the observations with WRF-CAM. And for CAM5 simulation, although CAM5 can capture supersaturation in clear sky and in cloud, there's still a lack of water vapor subgrade scale variability, and there are some differences in how CAM5 represent the correlation between supersaturation, ice water content, and liquid water content. So my goal for the next step is to test new subgrade scale parameterization for relative humidity in CAM5, and also to test observation constraint correlations between microphysical properties and aerosols in CAM5. Now with that, I would like to give you an advertisement. So if you haven't submitted your AGU abstract, and if you're still thinking about should I go or should I not, maybe take a look at the session that I'm hosting with Yang and Xiaohong and Jiwen. It's the session called Microphysical and Microscopic Properties of Ice Clouds and Mixed-Phase Cloud, linking in situ, remote sensing observations, and multi-scale models. So with that, I would like to thank you for your attention and answer all your questions. Thank you very much.
Thank you very much, Minghui. Do we have any questions? I'm sure we must have some. I'm just going to ask one question, and maybe we can start it. The first slide you had indicated that the forcing from clouds was a negative like 20 or something watts per square centimeter. So is that averaged over a day to account for shortwave reflection and then trapping at night?
I would believe it's at least for a year. It's from Chen et al. 2000. I don't remember how many years of satellite data they were using, but yeah, it was an annual average at least.
Okay.
Thank you.
More questions?
Could you go back to your second figure? I think it was. Oh, sorry, could you go back to your second figure?
Much better. All right. So let me know.
This one, yes. Yeah. Okay. So when you are looking at the three here, and you gave us an awful lot of information about frequencies of occurrence and so on, how frequent do these three regimes actually occur, would you say? If you can just condense it down to sort of the bare essence, is it 90% for the top one?
That's a good question. So for in cirrus cloud, temperature below -40°C, we see half for the first and the third row. So half of them, no supersaturation, only ice crystal. Half of them, coexisting supersaturation and ice crystal. For the second case, it's the interesting one. We actually, in Spatial et al. 2013, the group from MIT, Dan Cecil, he used the WB-57 from NASA flight campaign and combined with our measurement in HAPO, and we found a very small chance that our observation go beyond the homogeneous freezing line. So it's an indicator of if we don't even see much of the observation go beyond homogeneous freezing, it could suggest we don't often have the suppressed nucleation, which is clear sky already over homogeneous freezing but still not forming ice crystal. So I would say the first and the third are the dominant, and they are half and half. All right. Thank you, y'all.
Okay, if no more questions, let's thank Minghui.
All right. Thank you all for coming.